Hello everyone. Today we'll explore AVL trees. These are important data structures in computer science. AVL trees are self-balancing binary search trees. They keep themselves balanced automatically. This makes them very efficient for storing and finding data. What makes AVL trees special is their ability to maintain balance automatically after insertions and deletions. This ensures that operations like searching remain efficient even in the worst case. Throughout this presentation, we'll understand the mechanics behind AVL trees, including how they maintain balance and why this balance is so important for performance. AVL trees were invented in 1962 by two Soviet mathematicians. Their names are Georgy Adelsonvelsky and Yevgeny Landis. The name AVL comes from their initials. They published their work in a paper titled An Algorithm for the Organization of Information. This made AVL trees the first self-balancing binary search tree data structure to be proposed. A regular binary search tree can become unbalanced depending on the order of insertions. For example, if you insert elements in sorted order into a regular binary search tree, it effectively becomes a linked list. This makes searching very slow, with time complexity of O of n. AVL trees solve this problem by enforcing a strict balance condition. For every node in the tree, the heights of its left and right subtrees can differ by at most one. This balance property is maintained through a mechanism of rotations that we'll explore in detail. The result is a tree where the height is always logarithmic in the number of nodes. This guarantees O of log n time for search, insert, and delete operations. The key concept in AVL trees is the balance factor. For any node in the tree, the balance factor is defined as the height of its left subtree minus the height of its right subtree. In a valid AVL tree, the balance factor of every node must be -1, 0, or +1. A balance factor of 0 means the left and right subtrees have the same height. A balance factor of +1 means the left subtree is one level taller than the right subtree. A balance factor of -1 means the right subtree is one level taller than the left subtree. If any node has a balance factor with an absolute value greater than 1, the tree is considered unbalanced and needs to be restructured. When we perform insertions or deletions in an AVL tree, we need to check the balance factors of all affected nodes. If any balance factor goes out of range, we perform rotations to restore balance. The balance factor is stored at each node and updated after each operation. This adds some overhead, but ensures the tree remains balanced. When an AVL tree becomes unbalanced after an insertion or deletion, we use rotations to restore balance. Rotations are local operations that restructure the tree while maintaining the binary search tree property. This means for every node, all keys in its left subtree are less than its key, and all keys in its right subtree are greater than its key. There are 4 types of rotations: left-left, right-right, left-right, and right-left. The type of rotation needed depends on where the imbalance occurs and the balance factors of the nodes involved. Single rotations are for left-left and right-right cases. These are used when the imbalance is in a straight line. Double rotations are for left-right and right-left cases. These are used when the imbalance forms a zigzag pattern. Let's look at each type in detail to understand how they work and when to apply them. The left-left rotation is also called a right rotation. We use it when a node becomes unbalanced because its left subtree is too tall on the left side. This happens when a node has a balance factor of 2 and its left child has a balance factor of 1 or 0. For example, imagine a tree with 30 at the top, 20 on the left, and 10 on the far left. After adding 10, the top node has a balance factor of 2. Its left subtree has height 2, while its right subtree has height 0. And node 20 would have a balance factor of 1. To fix this, we perform a right rotation. Node 20 becomes the new root of this subtree. 10 remains as the left child of 20. 30 becomes the right child of 20. Any right subtree of 20 before the rotation becomes the left subtree of 30 after the rotation. This operation reduces the height of the left subtree and increases the height of the right subtree. It effectively shifts the weight from left to right and restores balance. After this rotation, all nodes have balance factors within the allowed range. The right-right rotation is also called a left rotation. It's the mirror image of the left-left rotation. We use it when a node becomes unbalanced because its right subtree is too tall on the right side. This occurs when a node has a balance factor of -2 and its right child has a balance factor of -1 or 0. For example, imagine a tree with 10 at the top, 20 on the right, and 30 on the far right. After adding 30, the top node has a balance factor of -2. Its right subtree has height 2, while its left subtree has height 0. And node 20 would have a balance factor of -1. To fix this, we perform a left rotation. Node 20 becomes the new root of this subtree. 10 becomes the left child of 20. 30 remains as the right child of 20. Any left subtree of 20 before the rotation becomes the right subtree of 10 after the rotation. This operation reduces the height of the right subtree and increases the height of the left subtree. It effectively shifts the weight from right to left and restores balance. After this rotation, all nodes have balance factors within the allowed range. The left-right rotation is a double rotation. We use it when a node becomes unbalanced because its left subtree is too tall on the right side. This happens when a node has a balance factor of 2 and its left child has a balance factor of -1. For example, imagine a tree with 30 at the top, 10 on the left, and 20 between them. After adding 20, the top node has a balance factor of 2. Its left subtree has height 2, while its right subtree has height 0. And node 10 would have a balance factor of -1. A single right rotation won't fix this because it would just move the imbalance to the other side. Instead, we perform a two-step process. First, we perform a left rotation on the left child, which is node 10. This moves node 20 up to become the new root of this subtree, with 10 as its left child. Any left subtree of 20 becomes the right subtree of 10. This transforms the tree into a left-left case. Then, we perform a right rotation on the original unbalanced node, which is node 30. This moves node 20 up to become the new root of this subtree, with 10 as its left child and 30 as its right child. Any right subtree of 20 becomes the left subtree of 30. This two-step process effectively redistributes the weight to restore balance. The right-left rotation is the mirror image of the left-right rotation. We use it when a node becomes unbalanced because its right subtree is too tall on the left side. This occurs when a node has a balance factor of -2 and its right child has a balance factor of 1. For example, imagine a tree with 10 at the top, 30 on the right, and 20 between them. After adding 20, the top node has a balance factor of -2. Its right subtree has height 2, while its left subtree has height 0. And node 30 would have a balance factor of 1. A single left rotation won't fix this because it would just move the imbalance to the other side. Instead, we perform a two-step process. First, we perform a right rotation on the right child, which is node 30. This moves node 20 up to become the new root of this subtree, with 30 as its right child. Any right subtree of 20 becomes the left subtree of 30. This transforms the tree into a right-right case. Then, we perform a left rotation on the original unbalanced node, which is node 10. This moves node 20 up to become the new root of this subtree, with 10 as its left child and 30 as its right child. Any left subtree of 20 becomes the right subtree of 10. This two-step process effectively redistributes the weight to restore balance. One of the main advantages of AVL trees is their guaranteed time complexity. All basic operations have a time complexity of O of log n, where n is the number of nodes in the tree. This includes search, insertion, and deletion. The tree remains balanced, so the height is always logarithmic. In the worst case, the height of an AVL tree with n nodes is approximately 1.44 times log base 2 of n plus 2 minus 0.328. This is still O of log n. This is a significant improvement over regular binary search trees, which can degrade to O of n in the worst case when the tree becomes skewed. When compared to red-black trees, another popular type of self-balancing tree, AVL trees are more strictly balanced. An AVL tree ensures that the heights of subtrees differ by at most one. A red-black tree allows for a more relaxed balance. The longest path from root to leaf can be at most twice the length of the shortest path. This stricter balance in AVL trees means that searches can be slightly faster because the tree is more shallow. However, insertions and deletions in AVL trees may require more rotations than in red-black trees, which can make these operations slightly slower. The choice between AVL trees and red-black trees often depends on the specific use case. If searches are more frequent than insertions and deletions, AVL trees might be preferable. If insertions and deletions are more frequent, red-black trees might be a better choice. AVL trees have several practical applications in computer science. They're commonly used in database systems for indexing, where fast search operations are crucial for query performance. AVL trees can be used to implement in-memory indexes that allow for quick lookups, insertions, and deletions of records based on key values. They're also used in memory management systems for organizing free blocks of memory, where the ability to quickly find a block of a certain size is important. In programming language libraries, AVL trees are often used to implement dictionaries and sets, where fast lookups are needed. They're particularly useful in situations where the data is frequently searched but not as frequently modified, such as in caching systems or routing tables in network routers. Some specific real-world applications include the implementation of the extension for file system in Linux, which uses a variant of AVL trees for directory indexing, and the Java Collections framework, which uses a modified AVL tree in the TreeMap class. To summarize, AVL trees maintain balance through rotations, ensure O of log n-time complexity for all operations, and are particularly useful when search performance is a priority. They provide a reliable and efficient data structure for many applications where balanced search trees are needed. For those interested in learning more about AVL trees, I've included some references here. The original paper by Adelson-Velsky and Landis from 1962 is where it all started. This paper introduced the concept of self-balancing binary search trees and a specific balance criterion that defines AVL trees. For a more comprehensive treatment, you can refer to Standard Algorithms textbooks. Introduction to Algorithms by Corman, Leiserson, Rivest, and Stein provides a detailed analysis of AVL trees, including proofs of their time complexity and implementation details. The Art of Computer Programming, Volume 3, by Donald Knuth covers AVL trees in the context of sorting and searching algorithms, with historical notes and variations. Algorithms by Sedgwick and Wayne offers practical implementation advice and comparisons with other data structures. Data Structures and Algorithms in Java by Goodrich and Tomasia provides a Java-specific perspective with complete implementations. These resources provide in-depth analysis and variations of AVL trees that we haven't covered in this presentation, including proofs of correctness, optimization techniques, and hybrid approaches that combine aspects of different tree structures.